So we are looking at finding the proximate area under a curve when the curve is not a nice function. Now, obviously, the diagrams here on all of these have a nice function, as did her example in our little video. However, we're learning a new concept, and so we're going to work with easier functions to do that. So what we're doing is summing up the areas of each of these rectangles. So make sure you understand each of the pieces. The change in x is the width of your rectangle, and the f of x1 is the length or the height of the rectangle, which, you know, when you think area of a rectangle is width times length or length times width. In this diagram, we're summing up in this particular equation the right example. We have f of x1, that's this height right here, and then the width is the change in x. And the width on every single rectangle will be the same, and it's calculated by this formula that we were just looking at, okay? And so we have the width multiplied by each individual height. So the height of the second rectangle, the third rectangle, the fourth, and the fifth for this particular one. Now, we don't want to have to write that out for 20 rectangles, so we have this notation down here that looks like a, I don't know, a funky looking E, okay? This guy right here, oh, I didn't want yellow, here we go, red, is called sigma notation, okay? And this is saying to sum up from the first rectangle to the fifth rectangle, the area of each of them. Okay, so this represents this whole thing written out. Okay, and then it's this little xi is talking about any particular x somewhere in the middle, right? Like any of them. This could be xi. If I didn't know how many rectangles there were and there was a bunch on either side, the ith rectangle is somewhere in the middle between the left and the right boundary, okay? All right, so we're going to work with this sigma notation today. All right, so here are some useful sigma notations and other sums. So sum of arithmetic series and geometric, that came from 20-1, okay? And those might come in handy, but mostly the ones that we really want to be looking at are these sigma notation ones. So if I had to come up with a sum of I from 1 to n, then I could replace it with this formula. That is equivalent. So if I was adding up 1 plus 2 plus 3 plus 4 plus 5 all the way to n, that's what this piece means. It actually can be written as n times n plus 1 on 2. And we have similar ones for if I have I squared. So 1 squared plus 2 squared plus 3 squared all the way to n squared. That's equal to this formula. And again for I cubed, okay? And so we will use those a little later in the lesson. And similarly, if I had to sum up a constant, so it was the sum of 4 for, n rectangles, 4 plus 4 plus 4. Of course, hopefully that makes common sense that you would have to go 4 times the number of rectangles, which would be your n value. Okay, so we're kind of going to do our own little investigation here with example number 1. So we're going to calculate the area under y equals x from 0 to 1. So I'm going to draw y equals x as best as I can. And I have 0 to 1. So I'm going to draw myself a boundary at 1, and hopefully you can clearly see that this just forms me a nice geometric shape. So I don't need strips for this question. It's a triangle. So to calculate the area of a triangle, it's half the base times the height. And so the base in this case is 1, and the height in this case would be, well, when x is equal to 1, right, f of 1, because this is my height up here, what would be y? Also 1, because my function is y equals x. So when I plug that in to my formula, I get an area of 1/2 times 1 times 1, which is 1/2 units squared. So that's actually its exact area because it became out to be a nice geometric shape. Well, let's approximate it with some rectangles to see how close we could actually get to that accurate 1/2 units squared. So in this diagram, we are using the right-hand endpoint as the demonstration, and we are dividing it into 6 strips. Okay, so we're still dealing with the function being y equals 2x. And so to approximate this area, we need the area of the rectangle number 1 plus the rectangle 2 plus 3 plus 4 plus 5 plus 6. So we need to add up all of these rectangle areas. In order to do that, I need to figure out what the width of each of those rectangles is and multiply by each of their individual heights, which is different. The width is the same. So the width is that change in x, which would be 1 minus 0 over the number of rectangles, which is 1/6, which you can clearly see on this diagram in the first one, but just to show you how the formula works. So every rectangle has a width of 1/6. So I have 1/6 for the first rectangle, and then the height of the first rectangle, this height right here, is going to be f of 1/6. And then, oh, that didn't quite get my brackets in the right spot. Sorry, guys. Here we go. F of 1/6. That's what I wanted. And then I have to add that. Oh, that's not what I wanted either. Sorry, guys. Okay. Then I have to add that to the next rectangle. So the next rectangle also has a width of 1/6. And then what would its height be? Well, its height is going to be f of, where are we at? 2/6. And so forth until we get all the way down, to the last rectangle, which also has a width of 1/6. And then the height on the very last one, this guy right here, is happening at that f of 1 or f of 6 on 6 if you like. Same idea. Now remember that f of x is my function. Okay, so f of x, this guy here, is equal to x. So f of 1/6 is just going to be simply 1/6. So when I'm doing this calculation here, this is going to be 1/6 times 1/6 plus 1/6 times 2/6 plus ... 1/6 times 3/6 plus 1/6 times 4/6. You get it? 1/6 times 6/6. And then when you very carefully plug that into your calculator, you could get an amount. One thing I would like to note before we do that, though, is to see that every single one of these has that width. So I could, in fact, factor that out, and then I'd have 1/6 plus 2/6 plus 3/6 plus 4, 5, 6, and 6/6. That's what would be left over. So that's one way to look at it in simplifying. And so what do we get here? We get that this is approximately equal to 21 on 36, which is 0.583 units squared approximately. So it's close to that 0.5, but not quite there. What happens if we make it be 12 strips of equal width? Okay, so now we have to find our area by adding up 12 rectangles, the areas of those 12 rectangles. So the width this time, hopefully you see, is 1/12. Okay, so the change in x is 1 minus 0 on the number of rectangles. And the reason why I have 1 is the left boundary is 1 and the right boundary is 0. And then divide by the number of rectangles, 1/12. So this is going to be 1/12 times f of 1/12 plus 1/12 times f of the next right boundary is 2/12 plus dot, 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 plus all the way until we get to the last rectangle, f of 1 or f of 12/12. And in this case, I can see that I for sure can take out my 1/12. That would make my life a little easier. So let's do that. So if I factor out the 1/12, I'm left with f of 1/12, which is 1/12, plus f of 2/12, 2/12, plus 3/12, plus 4/12, plus etc., all the way to 12/12. Well, in fact, I could actually factor out another 12th here. So I could take out a second 12. So we have our first 12, which is representing our width. And then every single fraction that's left over also has a 12th. And then that leaves me with 1 plus 2 plus 3 plus 4 all the way to plus 12. And this brings us to that formula right here. This is my I formula. I'm summing up 1 to 12. This is that sigma notation formula. Let's just go back a second. Right here. Okay. This is n plus 1 because I'm just adding up single numbers, 1 plus 2 plus 3. In this case, my n is 12. So what if I just use that to demonstrate in this example how we could tidy and simplify? So this would be equal to 1/12 times 1/12 is 1 over 144. So let's do that. And then this is using that formula. N is 12 times n plus 1, so 12 plus 1, all over 2. Okay, so I'm just going to write that over here. We have the sigma notation of I equals 1 to n of I is equal to n times n plus 1 over 2. Okay, that was the little formula that we used for right in here. And then, of course, we could actually find the number to all of this, which would be 13 on 24, which is approximately 0.541 units squared. So you see, as we increase our rectangles, as they showed us in the video very clearly, that we are getting closer to the exact area of our triangle in the first piece of this example of being 1/2. And of course, how could we increase the accuracy of this approximation? Well, hopefully you would know, increase the number of rectangles. That's how we're going to get closer and closer. Could we come up with a formula to represent the area if we had n rectangles? Okay, so let's think about this. We know from the last example, part C, with the 12 rectangles, that our area comes out to approximately the width being factored out. The width is actually 1 on n multiplied by f of 1 on n plus f of 2 on n plus dot, 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 all the way till we got to f of n on n. In the last example, n was 12. Okay? And then we know, because we're working with y equals x, that I could have this be equated to 1 on n plus 2 on n plus 3 on n plus dot, 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 n on n. And I could take out another nth from that last example and left me with 1 plus 2 plus 3 plus dot, 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 plus n. And then that was equal to, I'm running out of room. This would be 1 on n squared. And then this is our formula, n times n plus 1 on 2. And if I tidy that all up, I would get n squared plus n on 2n squared. I actually think I could take an n out there, n plus 1 on 2n. So I could come up with a formula for that particular example of y equals 2n, or y equals to x, sorry, for this particular function. So now the question is how do we relate this to limits? All right, so I'll come back in the next video.